All right, let's. Thank you for submitting the pre-test, everybody. Let's take a look at our pink sheet of notes. I didn't choose the pink; it chose me today, which is fine. I like the color pink. All right. So we're going to start on linear functions. Starting on linear functions. This is pretty good stuff. This is really where the foundation of first semester Algebra 1 starts coming in. So we're talking about straight lines, and we're going to figure out how the equations of straight lines works, and we're going to find out what the x and the y intercept mean in the context of the problem. We're going to figure out what the slope, which is the pitch of the line, means in the context of the problem. So pretest is done, and awesome. So let's move on. All right, so a few things. You've all seen this type of chart where you have input and output. You're putting something in, you're getting something out. So in this particular case, if we plug 130 in, we get 50 out. Thank you. All right. If we put 290 in, we get 210 out. And so they're saying that the rule is you subtract 80 each time. So if I had subtracted 80 to get here, what would this have been? Yeah, 100. Yeah? And then if I would have had to subtract 80 to get to that, what do you think? If I had to subtract 80 to get to that, what did I put in to get to that? 140. If I had to subtract 80, what did I get here? We have to add 40 to it because we had to subtract 80 to get to that, right? So if we add 80 to 340, what do we get to? 460? 260. No, it has to be bigger because you're subtracting. The left column you put in would have to be bigger because you're subtracting to get to the right column. 420? Yep. Okay, do that. So that's just kind of a basic input-output where they gave you a rule, you put something in, you got something out. This, if you had plotted the data, would form something called a straight line or a linear graph because there's a small mathematical operation that's taking place in order to get there. All right, so a relation. Let's see, do I have that? Any move on that? Nope. A relation is a set of numbers, so paired numbers. So you could have like 3, 7, 2, 8, things like that. Or you could have some sort of input-output, where you have a table. Okay, input-output. A relation. So every set of ordered pairs, meaning if you're using an ordered pair, you're trying to create a straight line, or you're trying to figure out on an XY axis where your point would exist. Any coordinated pair of a point, 3, 7, or if we had, like, say over here, we had 8, 2, that would refer to the point 8, 2. Okay? Anytime you have that, it's a relation. There are relations that are, some of them are special. They're called functions. And the function does a number of things. But the function in order for a function to work, you can't have anything drawn that a vertical line test wouldn't pass. Okay? Meaning if you draw a vertical line test anywhere on your graph, whether it's just dots or it's an actual picture, if the vertical line test touches the graph through one and only one point, your relation is a function. Let's write that down. Your relation is a function if a vertical line drawn touches graph only one time. Okay? So let's talk about ordered pairs. Would this value right here have an x comma y value? Would this have an x comma y value? Would all the rest of these all have x comma y values? Okay. So the x value tells you how far right or how far left to go, and the y value tells you how far up and how far down to go. Would that make sense if I stated it that way? Yeah. So, in order for you to have a function, the x value won't repeat. And if the x value doesn't repeat, that means the vertical line test passes. So if I drew a circle on a graph, is a circle a function? By what I've just talked about. Will a circle pass the vertical line test? No. A circle, the vertical line could touch it once if it was, you could kiss it, but it could touch it twice on circles. Okay? So, we're going to build a little bit more on it. Guys, you're talking a little too much. We're up here. Okay? So the domain, the range. Domain is a fancy way of saying x values. So the range is a fancy way of saying the y values. Okay? So if domain repeats, then your relation is not a function. Okay, so remember, every set of ordered pairs, every input-output, any domain and range is a relation. In order for that relation to be a function, you can't repeat your domain. You can't repeat your x. You can't repeat your input. Okay, so the domain and the range. Now, sometimes you're like, oh my gosh, how am I going to remember domain and range? How do I know that domain goes with x and range goes with y? Well, is x comma y alphabetical? Does x come before y in the alphabet? Yeah. Does D come before R in the alphabet? I hope so. If not, you're saying the alphabet song wrong, right? So, x comma y is already alphabetical, therefore domain and range are alphabetical as well. So now when you're like, oh my gosh, what did the domain go with? Oh wait, domain and range, that's alphabetical. Alphabetical, x and y are also alphabetical. So x goes with domain, y goes with range. That's be okay way to remember that? I hope. It's like one of the few things in math that they actually put some logical thought into. Maybe they didn't even think that. I'm sure if the mathematicians of the day did think about that, they'd be like, let's flip-flop it just to mess with society, so there's never a trick anyone could ever know. All right. So for each of the following examples, use the given relations values to fill in the other representations and identify whether or not the relation is a function and state why. So the best thing to do is we're going to take a look at all of our points. So maybe I just come up here. Let's pick. So this is the point 1, 2, 3, 4. Negative 4, 3. This is the point negative 2, 1. This is the point negative 2, negative 2. This is the point 1, 0. And this is the point 3, 2. So the domain are all the x values. And how do you organize the domain? Well, you try and have them in ascending order, so go from the least to the greatest. So what's my smallest x value up there? Negative 4. And then what would the next one be? Negative 2, and then negative 2, and then 1, and then 3. Agree? So, yeah.
If there's a C, could you just write negative 2, 1?
You can, absolutely. Now I'm going to cover that as well. So does everyone feel comfortable that these are the x values? -4, -2, 3, 1, and -2. And I wrote -2 twice. It happened up there twice. Okay? And then my range, we have 3, 1, -2, 0, and 2. And again, you want to try and keep these kind of matched up. It's not imperative, but you just want to say, okay, my domain encompasses these x values, my range encompasses these y values. Now the question was, if I had a number done twice, can I just write it one time? And the answer is absolutely yes. And I'm going to leave it up to you at this point if you want to write it just once or if you want to write it twice or however many times it happens. Okay, it's going to be your call. It's not right or wrong. In later math classes, they'll start fading out the repeat, but it's not incorrect if you have them both or if you just want to list it once.
Yes.
Okay?
No.
So, function or not?
No.
Why not?
Because if we do a vertical line test, we'll go straight down.
Okay, so what repeats?
Negative 1.
Which is what?
The
X, which is what?
The domain.
Domain. So domain repeats. And it only repeats once, and the vertical line test does not pass because if I draw a vertical line anywhere, like this one works, but then if I put a vertical line here, both of those touch. That one works, this one works, but because those two right there fall along that vertical line, that means your domain's repeating, your x values are repeating, your input's repeating. So the domain repeats. So is this a relation? Absolutely. Is this relation a function? No. Why is it not a function? Because the domain is repeating. Okay? Let's see. It asks for the ordered pairs, so we had them all, but we'll just rewrite them. -4, 3, -2, 1, -2, -2, 1, 0, and 3, 2. Okay, so we could represent them as ordered pairs. We could write our t-table, which goes exactly with the ordered pairs. Okay, so these are all just different ways of representing. So, anytime we have points, we have a relation. If we want that relation to be a special type of thing called a function, the domain can't repeat. X values can't repeat. The input can't repeat. Okay? Is this okay so far? Anything about this are like, oh, do. It's okay if you're there, but let me know. All right, example number 2. Oops, I don't know what this is. All right, so we don't have any points drawn, but we do have ordered pairs down here. Agree? So we can do a number of things. Oops, nope. Go back. We're on example 2, right? All right. So we could do this a couple of different ways. We could start filling out our t-table. So I know I have -2, 5, 4, 3, 2, 5, 3, -1, 2, 6. Does everybody feel comfortable how I went from these to this?
Yep.
Does anybody that doesn't make sense? Okay. We can easily fill out our domain. And again, you can have it in order, but you don't necessarily need to. So I might have -2. And I could have 2 and 2, and 3 and 4. The range, I would try and keep them in order, be important. So -2 goes with -5, 2 goes with 5, and 2 goes with 6, and 3 goes with -1, and 4 goes with 3. Okay? Just by looking at this, will it work as a function?
No.
Why not?
Because it's
Domain does what?
It repeats.
Mister, you put a -5. There's no -5.
right, we can plug our ordered pairs in and our graph. So negative 2, 5, 4, 3, 2, 5, 3, negative 1, and 2, 6.
Not negative, just 2, 6.
Oh, thank you, thank you, thank you. And then 2, 6. And I made the other one red for a reason. Why is that? Huh? It's off the chart, and this is also, these two are the culprits of why this relation is not a function. Agree?
Yeah.
Because if I drew that vertical line in, boom,
Oh.
it's not going to work, right? Cool. Okay. Am I going okay so far?
Yes.
Everyone kind of clear? Clear as murky water at least? Yeah.
It could be not a function, but a
Relation?
relation.
It is a relation, but there's special relations that are called functions, and those have to deal with when the domain doesn't repeat. Yeah,
If it was a function, the lines are straight.
that's okay as well. That's a great question.
What is it?
So if it, let's say this point didn't exist, let's say that one's not there. This is still a function. It's a relation, and it doesn't matter that they have dots all over the place, as long as the dots don't fall into the vertical line where the domain repeats. Okay? Yes, we are going to definitely get to linear, so straight line stuff, but at this point we're just plotting points and we're just trying to define a relation versus a function, or a relation, and it is a special relation called a function. May I move to the next slide?
Yes.
All right. All right. Oh, this one is a little bit different. Let's see. All right. So ordered pairs: negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. So the domain is negative 2, negative 1, 0, 1, and 2. The range is 4, 1, 0, 1, and 4. Does the domain repeat?
Yes.
Does the domain repeat?
Yes.
I have negative
No.
2, negative 1. Is negative 2 and positive 2 the same thing?
No.
No, is negative 1 and positive 1 the same thing?
Yeah, it doesn't.
They don't repeat. So is it a function by our definition?
Yes.
Yep.
Domain.
It is a function because why?
The domain doesn't repeat.
Domain does not repeat.
In the test, does it do or have all of this stuff and we have to do all that?
We'll see. We're just trying to get some. So the domain does not repeat. So some of you might notice that the range does repeat, but we haven't talked about that yet. We're just talking about justifying the domain. The domain has to do with the x values. And so what we can do is we start plotting our points. So negative 2, 4, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. So, oops. So, vertical line work, touches once, touches once, touches once, touches once, touches once.
Hey.
This relation is a function because the domain, which are the x values, bless you, which are the inputs, do not repeat. Yeah. This would form a parabola, absolutely. And that's more second semester, but we'll get there. Cool, good deal. We feeling okay so far?
Yep.
A little bit newer information. Some of it is common knowledge, but some of it's like, oh, okay, we're filling in a little bit more information to your knowledge. Yes? May I move to the next slide? Okay. So, come on, get away from me. Okay, is y equals 2x plus 3 a function? Why or why not? Ooh, think about the graph. What do you mean, think about the graph? Okay, so maybe we have some knowledge about how to graph a line. Maybe we've seen it before in other classes, maybe. So let's let's just think about this graph, okay? So I'm going to draw myself an XY axis. Do the best we can with it. I'll draw a vertical line, a horizontal line. Is that okay? Okay, so you might have known this, that this is the y-intercept. So at 1, 2, 3, we have a point. And you might have known that this creates a slope. So the slope of 2 is 2 over 1, which means I go up and right because they're positive from the point right here. So I'm going to go up 2, right 1. And connect these two dots to each other. That's what y equals 2x plus 3 looks like. And you're like, dude, wait. Where'd that graph come from? It's okay if you don't see it right away. We're going to learn how to use that a little bit more. But that's in slope-intercept form, meaning it gives the slope and it gives the y-intercept. So by what you know about a function right now, do you feel that this relation, which formed a straight line, is indeed a function? Yes or no?
Yes.
Why do you think so? Use the simplest terms you know. The vertical line test what? If I draw any vertical line anywhere on here, it touches my graph only once. So if that happens, that means the domain, the x values, don't repeat. Okay? The x values don't repeat. So is this a function? Yes. And then you could say domain does not repeat. Okay? Then, some of you might have noticed that they might have had some things written like that on the pretest, yes?
Yeah.
That's called functional notation. It's a fancy way of writing y. So what's the difference between y equals 2x plus 3's graph and function at x equals 2x plus 3? The graph looks the exact same. It's the exact same problem. Okay? So, how you want to call this is the function at x. It's called functional notation. Okay? So the function at x is how you say it. The function at x equals 2x plus 3. Then it says find the function at, this is no longer the function at x, it's the function at what? 6. So what? So rather than the function at x, the function at 6 is written this way. What had been right here in this equation? X. What do you think I'm going to put there now? 6. So 2 times 6 is? 12 plus 3 is? Okay? So the function at 6 gives me what y value? What do you think? 15, good. So it gives you a point. So this is related to that. Function at 6, you're plugging in your 6 for your x value, and then the function at 6 actually gives you a new output. Does this look a little different? This says the function at x is equal to 6. The function at x is equal to 6. The function at x is equal to 6. So let's think about what our original problem is. It's right here. Right here. Okay? So I had plugged 6 in for x here. So when I did this, I took 6 and I plugged it in right here, which meant it went in for any time I had x. This is a little different. This is saying f at x, function at x, is equal to 6. So the function at x, f at x right here, what am I going to plug in for this entire thing? What do you think? We're going to substitute f at x. Where's f at x over there? It's right here. What am I going to plug in for f at x? What am I going to plug in for f at x? 6. So I'm not substituting 6 in for x on this one. I'm basically saying, hey, f at x is a fancy way of saying y. So this is saying y equals 6. Okay? Again, this would have been a fancy way of saying what's happening at x. Well, that's in the y direction. So here, I'm going to take our original problem, which was this, f at x equals 2x plus 3. What part of that would be y in our equation? What part of this equation right here is y? F at x. Okay, so what am I plugging in for y? What am I plugging in for y on here? 6. What am I plugging in for a function at x up here? Plugging the 6 in. Okay, 6 equals 2x plus 3. Is this a little bit different problem than over there? And I'm sure this isn't the only time we're going to see this. So here I plug in a new x value and solve. Here I plug in for the entire f at x. So I'm plugging in 6. So first couple weeks of school, we showed how to do these type of problems to solve for x. What should I do? Good. Subtract 3. Take it. So 3 equals 2x. What should I do here now? Divide by 2. There you go. So this means x is equal to 3 over 2. Okay? So that is 3 over 2, comma, 6 for this. Yeah.
Where where the 2x plus 3 came from?
What was our original equation? 2x plus 3. So if I have function at something, if I'm going to change this inside the parentheses, that means it changes this to whatever that is. If this was function at smiley face, you're going to get 2 smiley face plus 3. But this over here said the function at x is actually equal to a value. So I'm going to replace f at x with 6 and then solve for that. That's like a big kind of like, whoa, this is way new. Where the heck did this guy just go? Okay, still here, it's newer information. Let's see if we move on and clear it up a smidge. Okay. Oh, look at this. Find the following. I have function at x equals negative 3x minus 2, and g at x equals 2x plus 2. Is there a difference between these? What do you think? It looks different, but is it different?
No.
They're both in functional notation. This is still y equals and y equals. Okay? What do you think? How do you think I do the function at 1? What do you think I do? Which one do I pick? F at 1. I picked the f one, right? So this is going to be negative 3 times 1 minus 2, which is negative 3 minus 2, which is negative 5. What about this one? Which one do I use? The f or the g one?
G.
G. So this is g at 1. Oops, I don't want that. So I'm going to use this other equation over here. I'm going to go 10 times 1 plus 2. Which function do I use here? F. Which function do I use here? Which function do I use here?
Oh, no.
How do I use this function? Which one do I use here? Okay, input, output, yes. For these last two, which function do I use here? The f or the g? I use the f. What am I going to do with this negative 8 though? Do I plug it in for x like I did on all these others, or do I replace f at x? I replace it with f at x. So this, right here, this goes in for it. Add 2 to both sides. Divide each side by -3. Done. Okay? Take a look at this one. Let's see the color I'm using. Let's use that aqua. All right. What am I plugging in here? What am I replacing? Which function? F or G? What am I replacing? What am I replacing? I'm putting 32 in where? No. G at x. I'm taking this right here, which goes here, and I'm going to replace that with 32. So I get 32 equals 10x plus 2. Okay? Subtract 2, so I get to 30.
Divided by 3 equals 3.
Divided by 10,
10
equals 3. So x equals 3. So, sometimes it'd be in parentheses. If you have something in parentheses, that means you're replacing the x. If it's still says f at x and it equals a different number, look, f at x is equal to -3x minus 2. So now we're saying that f at x is equal to -8. So we're replacing f at x with -8 or g at x. Okay? Let's see if we can sum this all up. Oh boy. We got time. Okay. 2 minutes.
No.
All right. All right. In the context of this problem, the domain are the x values. So what's the domain with this problem? Time. The range are the y values. So what's the range with this? Yeah. Okay, I want to show you where it's increasing. This is increasing here, here, and here. Okay, and we're going to talk about that a little bit more next time. It's decreasing here, here, and here. And then the maximum value of our function is the y component here, so that's our max. And our minimum value is right here. Okay, so I had to kind of finish up. Hang on, don't jump up and start running away yet. Okay, so it looks like if you do page 49 and 50, okay, and I'm going to put that number 15 and 16, just try. I know I went too fast through it for you to have a good chance for it. But page 49 and 50 is the homework for next time. Okay?
Monday? No.
That would be Monday.
So we have no homework.
Page 49 and 50.
Thank you.